Hi, in this lecture, we will be discussing about homogeneous reactions. So, homogeneous reactions are reactions that occur in a single phase. So, you are assuming that you have a uniform concentration and temperature for the whole system. So, basically, your system is your bioreactor again. So, although in reality, it's very difficult to achieve, or there are, of course, some parts that are not very uniform all throughout, but still we assume and we try our best to make the concentration uniform and as well as the temperature, of course, by using mixing. Okay, so reaction in homogeneous reaction, we apply reaction theory. So we have your two different aspects of the reaction theory: the reaction thermodynamics, which tells us how far the reaction can proceed, and the reaction kinetics, which tells us how fast your reaction occurs. So, for reaction thermodynamics, this especially here, we need to consider the equilibrium of your system. So, suppose you have a reversible reaction A plus B to form your products Y and Z. So, we express our equilibrium constant K equilibrium as your products over the reactant. So, you have Y raised to your coefficient Y times the concentration of your product Z raised to the coefficient Z over your reactant A and times your reactant B raised to the coefficient B. So, K-equilibrium, or rather your equilibrium constant, is a constant for that particular temperature. That means if you vary the temperature, of course, your equilibrium constant will also vary. So, we have your ln of K-equilibrium as equal to the Gibbs free energy over R times temperature, whereas the R is the gas constant. Or since the Gibbs free energy is equal to the enthalpy plus the enthalpy minus entropy times your temperature, so we can rewrite this equation as ln of K equilibrium is equal to negative delta H of reaction over RT plus the entropy over R. So from here, we can say that if you have an exothermic reaction, that is a negative delta H. So the first term of your equation, your negative delta H reaction over RT, will become a positive value, and if it increases, if you increase the temperature, you will have an increase in the denominator. That particular term will go down. So that means the K-equilibrium value will also decrease. And if that happens, since products, K-equilibrium is product over the reactants, the variation, or rather the production or the conversion of your product becomes lower. So in some cases, you need to also consider, of course, the conversion rate of your products by using your equilibrium constant. So the reverse goes for endothermic reaction. So increasing your temperature increases K equilibrium, so increases the product formation. So that is also those are the things to consider, especially when you design your reaction or your reactor. So if you have exothermic reactions, and of course your over time your system will have increasing temperature. So because sometimes the heat, if you do not have a proper cooling system, the heat will accumulate in your system. It will increase the temperature, and you will get lower and lower yield as the reaction proceeds. So those are the things to consider in designing reactions. Or rather, this is one of the importance of knowing reaction thermodynamics and as it applies to designing bioreactors. So an example here is the effect of temperature on glucose isomerization. So glucose isomerase is used extensively in the United States for the production of high fructose syrup. So this is a reversible reaction between glucose and fructose, whereas the enthalpy of the reaction is 5.73 kilojoules per gram mole, and the entropy of the reaction is 0.0176 kilojoules per gram mole per Kelvin. So we are asked here two things. First, we need to calculate the equilibrium constant at 50 degrees and at 75 degrees Celsius. And knowing that, if you have a company that aims to develop a sweeter mixture of sugars, that means that the mixture should have a higher concentration of fructose, because it is a sweeter sugar between fructose and glucose. So considering only the equilibrium, would it be more desirable to operate the reaction at 50 degrees Celsius or at 75 degrees Celsius? And also additional question from me. So when do you consider a certain reaction as irreversible? So this the question comes from our reference book, Pauline Doran's Bioprocess Engineering Principles, 2nd edition. Now, the solution. So, of course, from the given, it's in degrees Celsius, and most of our, thermodynamic calculations use Kelvin, so we need to adjust our units accordingly. So, convert the degrees Celsius to Kelvin. We have at 50 degrees Celsius, 323.15 Kelvin, and at 75 degrees Celsius, we had 348.15 Kelvin. And then again, since the equation that we are going to use is the equation ln of K equilibrium is equal to negative delta H reaction over RT plus delta S reaction over R. So we need to get the value of R. So we have the T. From the given, we have the enthalpy and the entrophies. We just need to get the value of R. And R here, the gas constant. Since we are using joules or kilojoules, so we use 8.3144 joules per gram mole per Kelvin. And then in order to, since the enthalpies and entrophies are usually in kilojoules, so we just convert the units to your kilojoules. So 8.3144 times 10 to the negative 3 kilojoules per gram mole per Kelvin. So we just plug in everything to the equation. We have your enthalpy 5.73 kilojoules per mole, so negative delta H reaction, over your R constant times your temperature plus the entropy over R. So ending up with the K equilibrium constant at 50 degrees at 0.98. The same goes for 75. So plugging in the values at our reaction, we get 1.15. So finalizing our answer. So since we are asked directly what are the equilibrium constants, so the equilibrium constant at 50 is 0.98, and at 75 degrees Celsius it's 1.15. So what are the units? The units is basically, if we look at our equation, all the units cancel out, so this is basically unitless. Now, the next equation, if you consider equilibrium only, at what temperature would it be best to operate the reaction? So, comparing the two, we have greater equilibrium constant at 75 degrees Celsius, and we say that we want a higher equilibrium constant because it will produce a higher product concentration. So, based on this data only, we can then say that it's more desirable to operate the reaction at 75 degrees Celsius. That is considering equilibrium only. If we consider all other things, we cannot just say it's better always at higher temperature. Because again, this is enzymatic reaction. We still also need to consider the activity of the enzyme. So the enzyme has an optimum pH and optimum temperature at which it works. So most of the time, we just use that optimum conditions for the enzyme instead of, well, basically we have that optimum conditions to use. Okay, so another aspect in homogeneous reaction we need to consider is the reaction yield. The reaction yield is the expression of the extent at which the product is converted to the reactants. So we have three basic definitions here. So the one, we have the true stoichiometric or theoretical yield, which is basically the yield that you have in your general chemistry reactions. So you have your basically the mass or the moles of the products form over your mass or moles of the reaction used to form that particular product. So this is basically the most ideal of the three definitions of the reactant yield. So for example, if you have a certain reaction that, for example, A to produce 2B, so the mass or moles of the reactant form is, for example, if you have 1 mole of A, you produce 2 moles of B. So your theoretical yield is basically the product form, which is 2 moles over the moles of the reactants used, so it's 1. So you have a value of 2. So if you had 100%, so you have 200% yield. So the next one is for the observed or apparent yield. This happens when you have your if there are any impurities in your system, such that your reaction is not there are two simultaneous reactions occurring, and the observed or the apparent yield is basically the base from the mass or moles of the product that you desired over the amount of the reactant consumed. Since two simultaneous reactions consumes the same product, so basically you're looking here is that how one reactant, or rather how one product is favored over the other. So it's a bit of a competitive type of behavior in the system itself. And then you have the gross yield. This is usually what is used in engineering calculations because it's actually the one that is most easiest to measure, of course, because we are just looking at how much of the product you got at the end of the reaction divided by the reactants you provide at the start of the reaction. So these are the different definitions for that. So the true stoichiometric or theoretical yield, as I said, this is the most ideal. So you assume purity and ideal conditions, and then you have your for observed and apparent yield. It happens if you have two simultaneous reactions occurring. You cannot. It's very difficult to purify. There is impurities in your enzymes or in your reaction itself, and there are byproducts that occur. And then you have the gross yield. So if you have incomplete conversion of the reactant, this is usually the conversion, the completeness of the conversion, by the way, cannot be seen using observed and apparent yield. Observed and apparent and even the true and stoichiometric yield, you can only see that when you look at the gross yield, because you are looking at the total amount of reactants you input in the system, and then the amount of the products you form after the reaction, of course, or after your operation. Now, that's for thermodynamics. So let's now proceed to your kinetics. So for our reaction rate, we have an irreversible reaction, A plus B to form C and D. So the rate of the reaction can be expressed as the rate of change in the concentration of a certain species over time. So if your species is a reactant, so it's a negative, the negative derivative of the concentration, the molar concentration M over dt. So basically, from here, we can just learn about the rates of each reactants and products. So we have the total rate, the rate in mass or mole per unit time. This one is useful in specifying production rates occurring during manufacture. And then we have the volumetric rate. So basically, this is just your total rate divided by the volume, because it's more easier to consider the volumetric rate, because in an actual bioprocessing plant, you're looking at the volumes. It's the one that's one of the more directly measurable content. So we also have a specific rate. It's the rate per quantity of enzymes or cell used in biological reaction. So the specific rate, we have your the differential, the change in the concentration or change in the amount of your species over time, times the reciprocal or divided by your enzyme or your concentration of your cells, X. So the units of enzymes are usually unit activity, which is the amount of enzyme that catalyzes one micromole of your substrate at optimum temperature, pH, and substrate concentration. So we have this is a basic review of rate kinetics. So we have your rate kinetic equation. Rate is equal to the rate constant, kinetic rate constant, K. So it's different from equilibrium constant, mind you, times the concentration of your species. These are your reactant species. So you have your order, which is just adding the exponents of each. We usually have the coefficients as their exponents. So A plus B is the order of the reaction. And we have your K, like equilibrium constant, although the kinetic constant is different from equilibrium constant. The kinetic constant also is affected by the temperature. And how is it affected? It's given by your Arrhenius equation. K is equal to A, the Arrhenius constant, times E, the natural logarithm E, over your energy over RT. So this is just a review of your rate kinetics. So I won't be discussing much kinetics here. So please look at the accompanying lecture in this in the lecture notes that I will provide. The video links there for your different rate equations for rate kinetics. And also, we will be discussing mechanism and kinetics, although this will occur in a separate video. But we also have a video link for a background or supplementary material on that. So that's it for homogeneous reaction.